Okay. So today we're talking about angles. We're going to start with vocab and then we'll do some calculations. There are a couple of things that we need to have common words for. So I'm going to start with drawing you a picture. And we're going to go through a couple pictures and label features of pictures so we're all using the same words. That first picture, we've seen that shape before. It's straight, it's linear. It has one endpoint, so it stops on one side and goes forever in the other direction. Does anybody remember what we call those? Any guesses? Do you remember how your voice boxes work? You guys are brilliant mathematicians. You don't even have a guess for me? A guess? No guess? What do we call that? That is a good guess, and that is close. If this part of the line was missing, it would be a line segment. But because it keeps going in only one direction, it's not a line segment, and it's not a line because lines go forever in both directions. This is like half a line. The question is, what do we call half lines? The answer is that we call them rays. That is a ray. Like a ray of light, it comes from the sun and keeps going and going forever until it hits something. Yeah. And like everything, we need to be able to give it a name. Does anybody have a suggestion for a name for that ray? We could call it Thomas, but based on the features of that specific ray, looking at that ray, does that look like a Thomas? I don't see any T's up there. Yeah, A and B is probably good letters to use. Ab or Abe. I need to tell people that ab is a ray and not a line or a line segment. So I'm going to draw a little ray above ab's name. Can I call that ray BA? No, BA would point in the other direction. So for ray names, because they only extend in one direction, it's really important that we list the end point first. So this point here is called the end point. And it's always the first letter in the name of the ray. And rays should have two letters, right? The first point tells me where it starts. The second point tells me which direction it's pointing in. Yeah? So 2 points. First point is the end point, it's where it starts. Second point defines which directions it's pointed in. Why are we talking about rays? The answer is I need two of them to make an angle. An angle is formed by two rays with a common endpoint. I swear I know how to write. So two rays form an angle. As long as those rays meet at a common endpoint, we get an angle. Could be a skinny angle, could be a fat angle, could be an upside down angle. Two rays form an angle. Yeah. And there's a couple things we should keep in mind. First, when we have an angle, I should indicate which way the angle goes. Is it an angle from the bottom up, or is it an angle from the top down? So when we label angles, we don't just use a little curve to mark the angle. We put an arrow to indicate the direction you should measure it in. So I'm going to pull an arrow that way. That's my angle. Happy face. I'm hoping none of this is groundbreaking. And the angle has a common point where those two endpoints meet. And that common endpoint gets a name. The common endpoint that forms the corner of the angle is called its vertex. So the vertex of this angle is A. No, B. Because it helps if I look at my own picture. So far, so good? Yeah. And just like rays, we need to name this thing that's on the page. What could I name it? Not Thomas. Something from the picture. What could I name it? ABC. That's a good name. ABC. I heard CBA. Ooh. BAC. Are those things all the same? So which point is the vertex of the angle? B. So this guy doesn't belong. We need this common endpoint to be in the middle of the name. So ABC is fine, CBA is fine. They describe the same angle. If there aren't any other angles in the picture, if it's just this by itself, I could be super lazy and just call it by its vertex. I could call it angle B. All of those describe the same angle. I need to let people know that that is an angle and not something else. So like the boring mathematicians that we are, we just draw a little miniature angle in front. Angle ABC, angle CBA. Yeah. The reason we're going over that is because as mathematicians, yeah, we need to be precise. If I write 3 letters on a page as a mathematician without any other clues, that could be this, but it also could be this, which is a straight line. It could be, if I just list points A, B, and C, the entire plane that contains all 3 of those points. It could be the flat plane that contains those 3. So I need the symbol in front. Yeah? Symbols are important. And I just deleted a whole bunch of stuff. Okay. So far, so good? Yes? Okay. So next thing we're going to talk about is measuring angles. And we have a few more vocab words to go over, and then we're going to do some actual calculations. Yeah? So bear with me. I'm going to draw another picture. Okay, so first thing in that lovely picture of an angle, when we label an unknown side length or an unknown number, we usually use x. Yeah. When we measure an angle, and it's an unknown angle, instead of using a letter from the English alphabet, we're going to pull a letter from the Greek alphabet. And the default is theta, the circle with the line through it. Doesn't have to be theta, just like it doesn't have to be x, right? We can use A, B, D, S, Y for an unknown number. We can use theta or alpha or beta or gamma or whatever Greek letter you want to use to represent the angle. Theta is the default because it's easy to draw, and it sticks in our brain. The sides of the angle get labeled depending on where we start the angle measurement and where we stop. That has to do with this little arrow we drew. Where we start the measurement is called the initial side. How many people in the room have used a protractor before? The little half circle, I see a couple hands. The initial side is the side that you line up the bottom of the protractor with. You put the center at the vertex. The side that we stop measuring at is called the terminal side. So we start 0 degrees at the initial side, and then we rotate up to the terminal side. And however many degrees we rotated through to get to the terminal side, that's our angle. Lots of words. If I want to talk about the angle, we know we call it angle A, right? We label angles by their vertex. If I want to talk about how big the angle is, we label that as the measure of angle A. So angle A itself is the name. Stick an M in front. Now we're talking about a number, the measure, the size of that angle. Room 111, Mr. Jala speaking. I'm good. How are you? I do. Yeah, I'll send him down. Bye. We need you at 612. Okay, where was I? Oh, yeah, M. M means measure. So if I say just angle A, I'm talking about the shape, the picture. I stick an M in front of it, I'm looking for a number answer. In this case, I don't know what the number is, but I know that that unknown is called theta. Those are numbers. And at some point you learn to use a protractor. You can measure the angles. We're going to learn to recognize a couple by sight when we learn about the unit circle tomorrow. We can measure those angles two ways. We can measure them the way it's marked this way, which is from the bottom up. So starting here and going this way. No. Am I looking at that picture right? Yeah, I am. No? I'm having delusions of I'm facing it weird. Would be this way from my direction. Notice that that is opposite what a clock hand does. Clock hands, if I was looking at a clock up here, clock hands would start at noon and go this way. This is starting at 3 and going this way. So we call it counterclockwise. That is a horribly long English word. I don't ever want to have to write it again. So you will often see mathematicians and physicists write CCW for counterclockwise. If you measure an angle counterclockwise, the number you get will be positive. In other words, counterclockwise is the default. Mathematicians by default go counterclockwise in a coordinate plane. We start at the positive x and then we rotate up towards y. That's a positive angle. If I had drawn this arrow the other way so that it rotated the same way a clock hand does, that would be clockwise, or CW for short. And if I am rotating backwards, what do we think happens to that angle? It's negative. Yeah, flip sign. Theta would be negative. So if you're reading an angle measure that's given to you, that sign on the number tells you which way they turned. Did they rotate up or did they rotate down? If you're writing an answer, you need to pay attention to which way you turned. Did I go counterclockwise or did I go clockwise? Yeah. Okay. Whew. One more word. We're almost done. The last word is something called standard position. Words are hard. Right? Angles can sit anywhere in the universe, but if we say an angle is sitting in standard position, that means something very specific. It's telling us two things. First, that its vertex is at the origin. The angle itself is sitting right smack in the middle of the coordinate plane. And that its initial side sits on the x-axis. Specifically, the positive x-axis. The terminal side can sit anywhere else in the coordinate plane, but the vertex is at the origin, and we start on the positive x. For example, I want to build an angle that is in standard position. Somebody give me an angle measurement in degrees. How big do we want this angle to be? 45. That's an easy one to draw. Thank you, Daniel. I appreciate that. So if I want to draw 45 degrees, I'm going to put, for standard form, my vertex right here. Yeah. And I know my initial side should be on the positive x. So the first ray that forms one side of my angle is on the x-axis. My terminal ray should be sitting 45 degrees from that. And I know that x to y, what's that angle measurement? 90. 45 is half of 90, so I want to cut that angle in half. So my terminal should sit right about here. Ish. Probably not my best 45-degree angle freehanding, but we'll go with it. That is an angle in standard position. Yeah. The reason that's important is because we are going to be working almost exclusively with math in the coordinate plane. So when we talk about angles, we are generally talking about angles that are in standard position. One of the two rays sits on the x-axis. All right. Questions before we move on to the last little chunk? No? Everybody's cool? Okay. So let's talk about actual measurements. There are two units we can measure angles in. The first one is degrees. That's probably been your default in most math classes up to this point. And then you hit like math 3 and you started learning about trig, and you probably learned about the other measurement. What else can we measure angles in? Starts with an R. Radians. Very good. Daniel's on fire today. In trigonometry, in calculus, in physics and engineering, degrees are no longer the default. Radians are the default. There are a lot of equations, particularly in trigonometry and in physics, that don't work if the angle is in degrees. The angle needs to be in radians. So the question is, how do I get back and forth between them? Because oftentimes you'll be given degrees, you need the other thing. So we're going to do a little bit of thinking, and we're going to start with a shape we're familiar with, which is a full circle. How many degrees in a full circle? 360. Very good. 360 degrees. And I also know that a full circle in radians is 2 pi. So 360 degrees must be equal to 2 pi radians, because they both measure the same thing, a full circle. And we're going to use that to build our conversion factor. Both of those numbers are even numbers because they are divisible by 2. So let's divide them by 2. What is 360 divided by 2? 180. What is 2 pi divided by 2? Pi. Perfect. And as far as converting back and forth, this is our conversion standard. Yeah. And I'll show you how it works both ways. Before I do, I'm going to go one step further and divide both sides by pi. And I want to say 57.3, but I have to look. Yes, yay, I have a memory. If you divide both sides by pi, you get approximately 57.3 degrees for every 1 radian. So degrees are tiny. It takes 360 of them to make a full circle. Radians are huge, right? They're not quite 90, but they're almost a full quadrant. You need 2 pi of them to make all the way around. I'm going to write little squiggly equal signs between them because that is a rounded number, right? Pi goes on forever. So when we divide by pi, we get a number that goes on forever. You should not ever, as a mathematician, use this to do conversions. This is rounded. You will get a rounding error in your answer. Use this guy. Yeah? How many what, huh? 3.1415926. That's as far as I got. Yeah, no, I don't like memorizing things for the sake of memorizing. I did have a freshman girl at the last high school I taught at. We had a competition because we had a math club, and every pi day we'd have a pi recitation. Words are hard. Competition where you'd see who could recite the most numbers. She got past 300. Yeah. She said she had an app that taught her one new number a day, and that's like all she did her freshman year. Yeah. I am, alas, not that dedicated to memorizing for memorization's sake. Okay, so we're going to practice going both ways. We'll start with degrees to radians. And if I want to get from degrees to radians, I'm going to multiply my angle by a fraction. And the question is, what goes in the fraction? And if you've had Miss Lark for science class, she may have taught you about stoichiometry and the joy of unit cancellation. That's all we're doing here. I want to get rid of degrees, and the degrees are in the top, so I'm going to put degrees in bottom. 180 degrees, because degrees on top and degrees on bottom will cancel. Gets rid of the unwanted unit. Yep, and 180 degrees is equal to pi radians. Put pi on top. That fraction is equal to 1, because those numbers on top and bottom are measuring the same thing, the angle that forms when you have a straight line. It's the same physical quantity on top and bottom, so that fraction is 1. I'm not changing the number, I'm just changing its units. It's not cheating, I promise. Before we do the examples, let's do the reverse. I have radians, and I want to go 2 degrees. Any guesses what I'm going to multiply by? Very good. More specifically, the reciprocal, the upside down version. Yeah, we're going to flip it. So instead of pi on top, now pi's on bottom, because I want to cancel the radians. And the degrees are on top, because that's what I want left. Units you want to get rid of on bottom, units you want left on top. I'm going to do a bunch of examples. I'm trying to be consistent here. Okay. So let's start with 60 degrees. I want to convert 60 degrees to radians. And I am a good boy. I know how to follow directions. It says multiply by pi over 180. And if you are lazy, you can plug that in your calculator, bless you. I would not recommend doing that, because when you are giving an angle in radians, you want to give an exact answer that will contain pi. So you should reduce and then multiply the fractions. So that's what we're going to do. I know whole numbers are fractions over 1. And I know when I multiply fractions, I can cross cancel between tops and bottoms. Yeah. And then I multiply across the top, multiply across the bottom. And the first thing that I see that cancels are the units. Yeah. Degrees on top, degrees on bottom go away. I've got radians in my answer. I'm happy now. I just got to deal with the numbers. What divides evenly into 60 and 180? 6? Yeah, you can say it out loud. Yeah, 60. How many times does 60 go into 60? Once 60 goes, my pen works, 60 goes into 183, because 6 goes into 18.3. And then we multiply. So 1 times pi is pi. 1 times 3 is 3. Pi over 3 rads. Yeah. Not too bad. Yeah. Try another one. 90 degrees. Oh, you were lucky. I was about to call on you. LD, can you tell us what we should do first? Very good. Multiply by that unit conversion fraction. Yeah. Very good. Next step. Melissa, what should we do next? Degrees cancel out. I'm going to do that. Very good, very good. Sam, what should we do next? Okay, so those cancel. One of those, two of those. I'm implying to agree. Pi over 2 radians. That's perfect. Very good. There are 4 measurements that you should absolutely have memorized, right? We know that we start at 0. The x-axis is pi over 2. That's 90. Every other axis is another pi over 2. So pi over 2, if I add another pi over 2, that's pi, because that's now a straight line. And then 3 pi over 2, and then all the way back around is 2 pi. Yeah, those 4 you should have down. We're going to add to that tomorrow when we start looking at the unit circle. There are important angles that you should just know those conversions because they pop up so often. Yeah. Okay, one more. I want you to try it in small group. 135 degrees. Convert that to radians. Start with the obvious. That guy ends in a 5. That guy ends in a 0. Anything that ends or a 5 or a 0 is divisible by 5. So start reducing by 5, and then see if you can reduce by something else after that. Make the bigger numbers more digestible. Good, didn't you? Yeah. Where are we at? Okay, that's perfect. So now you're looking for numbers that fit into both evenly. Start small. If we can get these numbers down to more digestible sizes, it'll be easier. So the first thing I do is look at the end. That guy ends in a 0, so he's divisible by 5. That guy ends in 5. He's divisible by 5. So divide top and by bottom by first by 5 and see what you get. Because I think those will be more digestible once you do. Good. Very good. I see some good work. Okay, Brittany, what do I do first? Pi radians over 180 degrees. That seems to be what happened at everybody's table. That's very good. Aurelie, what do you do next?
So I checked like how many times you could put 135 and 180, and I think it was 1 and 0.333.
So that guy doesn't divide evenly into that guy. So you tried to reduce. You started looking at reducing. What does go evenly into both? 5. Yeah. So let's start with 5 because it ends in a 0 and a 5. So 135 divided by 5, 27. That's a less scary number. And 180 divided by 5, 36. Those numbers are less scary to me. They're both divisible by something. 9. Yeah, they're both factors of 9. So that, not factors of 9, multiples of 9. So that guy is 3, that guy is 4. I agree. Did anybody else get 3 and 4? I see some nodding, some thumbs up. Yeah, good. And those are done because this guy's prime and he doesn't go into 4. So 3 pi over 4. So 2 suggestions, because you're going to notice on your homework and on your quizzes and tests, they're going to ask for exact answers. That means fractions, not decimals. If they are big numbers, start with what you know goes in. Test 2, test 3, test 5. Because if you can get it down to numbers you recognize, it'll be more easy to digest. Yeah, you can do multiple cancelizations. Second, if you are absolutely stuck, ignore the pi, just divide the numbers, and then use the math frac button to convert it back to a reduced fraction. So on your calculator, you can type 135 divided by 180 and hit enter, right? Top divided by bottom, and I get 0.75. And if you press the math button, you'll notice the first thing is an arrow fraction, and if I hit enter, it'll say answer to fraction on my screen, and hit enter again. It tells me that converts to 3/4. So if you know fractions are a weakness and you struggle with reducing, make friends with that math frac function on your calculator. Yeah, it's 2025. There's a reason we have technology. Okay, reminders that when Delta Math and your textbook and your tests say exact answer, that's the kind of answer they're looking for. Yeah, and if you're given an angle that doesn't have units on it, and it's a fraction with pi floating around, the units are radians. Only radians are going to be given to you like that. Okay, I see a couple of gloomy looking faces. How are we feeling? Kind of okay? A little bit okay? Nobody's going to run screaming and drop the course, right? Okay, let's try going the other way. Yeah, same deal, except now, if I scroll back up, we're going radians to degrees. So our fraction is flipped. Now it's 180 over pi. Yeah? So let's start with, stop moving TV, 5 pi over 4 radians. I want to convert that to degrees. Same process. Multiply by my unit conversion fraction, reduce, get my answer. Yeah. So multiply. In this case, the fraction's upside down, 180 on top, pi on bottom. I don't have to put anything over 0 because my first value was already a fraction. Yay. I just got to cross cancel. Does anybody see something that's going to cancel in those fractions? I see a couple of things. I heard a pi. I agree there's a pi on top and pi on bottom. Those are going to cancel. What else? Radians. Yeah, the units cancel, leaving me with degrees on top, which is what I wanted. And now I'm just left with a 5 and a 180 on top and a 4 on bottom. So the question is, does 4 fit into 180? And we check on our calculator. I'm pretty sure it does. What's 180 divided by 4? 45? So 1 and 45. And now I've only got 1s on the bottom, so I'm done. This is going to be a nice, pretty whole number. I multiply across the top. 5 times 40 is 200. 5 times 5 is 25. So 225. Check my math on a calculator, please. It's been a long day. Okay, we're going to try one more. Eight pi over 7 rads. I want to convert it to degrees. All right. Natalia, what do I do first? Perfect. Multiply by 180 over pi. That's our conversion fraction. Yeah. Next step. Gabby, what do I do next? Right idea. Cancel the units. In this case, rad on top, rad on bottom. Perfect. What else can I cancel? Pi on top, pi on bottom. Perfect. And then we look at the bottom and it looks sad because I've got a 7 down there, which is a prime number. Does 7 divide evenly into 180? No. Which means that I'm going to get a fraction answer that has 7 on bottom. I need to know what 8 times 180 is. And I'm pretty sure it's like, 4,000 something. Yeah. There we go. 1448. 0. 144. I knew there were 4s in there somewhere. And this is degrees. That's an exact answer. With degrees, we usually round. We can convert this to a decimal on our calculator. When you round, you should use the squiggly arrow or squiggly equal sign to indicate you rounded. And I'm going to do that right now. So 1440 divided by 7, 205.7. So that's another point that's going to be a little bit tricky. When you are giving an answer in radians, there's going to be a pi floating around. You can't make that any prettier. Give me a fraction with pi in it. If you're going to degrees, which doesn't have a pi floating around, you can give me a rounded decimal. So radians should always be nice, pretty, accurate fractions. Decimals, or degrees, you could go to decimal. Yeah. Okay, before I set you loose for today, a reminder that when you log into Delta Math to do your homework, pay attention to the wording in the question. If it says exact answer, don't give it a decimal. It wants the fraction. If it doesn't say exact, rounded decimal is probably fine. Follow the rounding directions, yeah? Okay, good work today. Tomorrow, we're going to pick up where we left off, finish 5-1, start 5-2. Yay. If I'm going too fast or too slow, please give me feedback because, again, you guys are the guinea pigs for my first trig class. I haven't taught it as separate from pre-cal before, and it feels a little weird.